recording here now. So I need my recorder. In my other class, someone's like, "You're not recording, sir." So anyway, I might do a little voiceover of that first part. So from before, the old one, if we look at a bad example, there's several ways to get bad examples, maybe. One is certainly y equals 1 over x, where x is approaching 0. So on this one, maybe I'll just draw the sketch here, is we know that this thing looks like this. So there's our graph. And if we looked at x equals 0 here on the graph, if we come in from the right, the limit as x goes to 0 from the right-hand side, as we're getting closer and closer and closer and closer to 0, the y values are getting huge. So the limit of this thing would be plus infinity. You could say it doesn't exist, but plus infinity is sort of the more technical thing. And then down on the other side, if we pick values that are getting closer and closer to 0, but on below, those y values are getting really big but negative. So we would say that the limit as x approaches 0 on the left is negative infinity. So clearly these numbers, they're not numbered to begin with, and the values, the result is not the same. And so we would then say the limit as x approaches 0 by itself doesn't exist. So DME does not exist. Because those are different. Those are different. You can also say, well, look, I mean, f of 0 doesn't exist either, because there's an asymptote there, and so there's no chance of it being continuous. There's a solid break in the graph. So that's where the limits don't line up. Just pictorially, we could do something like this, where the graph comes along and then for some reason has a hole in it and then comes along like that. So in that particular picture, the limit is okay because they're both from either side is approaching this height, which is the limit's always the y value. So the limit's okay, but the value doesn't exist because there's a hole in the graph. So you could have a limit and it works, but it's not continuous because there's a hole. And then finally, we would draw pictures like this, where the graph would be coming along, there would be a hole, then there would be a point, and then there would be a hole, and then the graph would continue along like that. So in this case, if you're coming in from the right, you're going to be up here. This would be like the limit as we approach. We'll call this like A here. If we approach A from the right, we'll get this height. If we approach the limit from the left, down there, the limit from the left will be a different value. And then the actual function value would be at a third point. So this is like a jump to the point and then another jump to continue the function. It's called a jump discontinuity. The limit doesn't exist because we get different values. The value of the function is okay, but none of that stuff lines up. So it's clearly not continuous. So it's always good to refresh on that kind of stuff before you jump into something that's a little more complicated. So now, is we want to talk about what does it mean to have x, y approaching a point. And we'll just pick 0, 0 as our point. So, so we can't just talk about approaching from the left and the right because now we're sitting in the xy plane. We have x and we have y, and we have the point 0, 0, and we need to approach it. So the question is how many different ways can you approach this point? And the answer is, well, there's infinitely many. So you could come in sort of diagonally here. You could approach that way. And what's happening on that path right there? Well, on that path right there, it looks like we're talking about the line y equals x. And if that's the case, and the x is approaching 0, but all the values are positive, so there's actually two conditions now. You would say not only is x coming in from the positive numbers, but y and x are the same because they're coming along this diagonal. So that's one approach path, and we are getting closer and closer and closer to 0. If we come in from the bottom, for example, line here, this approach path, what's happening there? Well, the y values are going to 0 from negative y values. So that's definitely coming in with y negative values. But there's another imposed condition, is that x is 0. So every single point on that line, because it's the y-axis, so we have these two conditions. X is 0, and y is going to 0 from negative values of y. Or from the left, you could think, as far as y is concerned. And similarly, we could try this approach path here. Is what's happening on that line? Well, for sure, x is going to 0, but with positive numbers. We're coming in from the positive side as far as x is concerned. But there's also the imposed condition that on that particular path, y is 0. So there's three possible approach paths to get to 0. Now the problem is if the limit as xy goes to 0, 0 is going to exist, then you have to get the same answer no matter which direction you come from. So if the limit is going to exist, all limits on all approach paths have to be the same. Which stinks, because there are infinitely many of these things. So I think in practice, you probably wouldn't do that. It's like, hey, let's check every single approach path, figure out what that limit is. It was so much easier before when we were just like, look, let's just check from the left and the right, and if they're the same, we're golden. But we can't do that anymore. We have to approach all of these things and see what the z values end up being. If they're all the z values the same, then you would say the limit exists. So this is where the technical thing is I'm just going to actually sort of write it in words. So if we have the function c equals f of xy, and we're looking at the point 0, 0, then we say that the limit as xy approaches 0, 0 of z exists if, and this is technical, it gets more technical than what I'm going to write, but I'm just going to sort of write it in words. So it's if whenever 0, or whenever xy is close, in the technical term there, the technical term, is close to 0, 0, then z is close to, and we'll call it some value L here. I kind of want this to be that limit here. So if you get closer and closer and closer, no matter which direction, so now you can talk about like a radius around it. Like if I'm within a radius of 0.001, then z is really, really close to a fixed value on the other side. And this is kind of what we did in the other section anyway. If you got closer and closer and closer and closer to 0, all the y values ended up being closer and closer and closer to the same thing. So this is also the idea. Is if you're really close, no matter which direction you are from the origin, you get really close to that, plug that value into your function, that z is going to be really close to the same L. And we would just write the limit as xy goes to 0, 0 of your z L. But still, this is not easy to show for a general function. Most of the functions you know, polynomials, most trig, all the trig functions, logs, as long as you're in the domain, all those things have no breaks. Coming up with things that do have breaks is tricky, but they still occur. They still can occur quite a lot. So, for example, the one that I wrote at the beginning. So let z equal x squared minus y squared over x squared plus y squared. So near 0, 0. What's happening to this? We know that 0, 0 is no good. You can't plug in 0, 0 because the top and the bottom would both be 0, and that's not fine, or at least indeterminate. So let's look at what happens as we approach 0, 0 along different approach paths and see if we get the same answer or if we get different answers. It's hard to tell, like right from there. Plug in really small values for x and y. Do we get a common value no matter what those small values are? So let's just try something like maybe from top. So we'll call this like approach path 1. So on approach path 1, what's happening? Well, we are coming in. We are coming in through points where y is going to 0 from positive values. So we're definitely coming in from positive y values. But like I said before, you also have a condition that on that approach path, x is always 0. We're coming in along the y-axis. And so if we took that and then imposed it to figure out what y is, or to figure out what the limit is, that particular limit would look like this. It's like 0y is approaching 0, 0 from the plus side. So x is equal to 0, and y is approaching 0 from the right. So what would happen if we put that into our function? Well, x is 0. We're saying along this approach path x is 0. So come back to your function. What happens if x is 0? We get 0 minus y squared over 0 plus y squared. And now, since everything is condensed down except for y, this becomes back to one of our original limits. There's no more x's and y's in there. There's no more x's in there. So we can just say the limit as y goes to 0 of negative y squared over y squared. And then now we're back in Calc 1. So if you want to compute a limit like this, you can plug in values that are really close to 0 and positive. But you also can go, wait a second, I know that y is not 0 yet, so I can always cancel y squared over y squared. So y squared over y squared is 1, and that's because y is not equal to 0 yet. Because I'm coming into 0. So I can cancel these out and I get negative 1, and therefore that particular limit is negative 1. So if you were to look at this graph, as you come in along approach path 1, the z values are going closer and closer and closer to negative 1. So maybe that is my limit. Hang on just a second. Sorry. Okay, so sorry about that. So maybe the answer to this limit is negative 1, because I got it when I came across this approach. Well, let's just try 2 more approach paths here. What happens if I try to come in towards closer and closer to 0, 0 along this approach path? So all we do is we look at what the conditions are, try and turn that limit into a limit back in Calc 1 and calculate it. So here that happens. So on 2, coming in, we're picking points on that one closer and closer and closer and closer. So definitely the x values are getting closer to 0 from the positive side. But along this path, y is always 0. So we've restricted it to just coming in on the x-axis. This is our new restriction here. So we just try and do this limit again, but under this new setup here. So the limit is now going to look like x, y is 0. So we're coming in to 0 from the positive side for x, and we're stuck at 0 for y. So what happens if I go back to the function and I impose y equals 0? Because I'm on that path. So if y is 0, you just get x squared minus 0 squared over x squared plus 0 squared, plugging that into the function. So if I just simplify that down, with x's, I just get the limit as x goes to 0 from the plus side of x squared over x squared. And again, x is not equal to 0, so I can cancel when x is not 0, and I will get 1. So if we come in from the top, it looks like the value of the limit should be negative 1. If I come in from the side, then it looks like the answer should be 1. These are not the same. So we would conclude that the limit as x, y goes to 0, 0 of your function z does not exist. Because in order for them to exist, all these limits have to be the same. And they aren't. So we picked 2, we got 2 different answers, so that's good. That breaks it. It's like the limit from the left and the limit from the right don't agree, so we don't have any limit. We don't have to do any more work. Trying to show that something actually does have a limit is a lot harder than showing something that doesn't. You just have to break it with 2 points. So let me try one more of those to see. Example, limit as x, y. 0, 0 is an easy one to check just because otherwise the forms get a little bit too big here. X plus y over x squared plus y. I don't have a subtraction here now, so maybe things are nicer. But that square in there is like, that might cause problems. So let's just see what happens as we approach 0, 0 from a couple different approach paths and see what kind of answers we get. This one will actually, let's try 3 of them this time. It won't matter, but just for practice. Let's come in from the top, come in from an angle now. So what happens if now if you come in from an angle, and then once again, let's just come in from the right and see what kind of answers we get. So we have 3 approach paths. So the first one we've already done. We're coming in from positive y values, but we're on the y-axis, so x is 0. So on this one, y is going to 0 from the right, but x is 0. So that's one approach path. On this, let me write down what these are, and then we'll do them. On the second approach path, now what's happening here is we're stuck, assuming this is the diagonal line, one slope of 1. We're coming in along the line where x and y are the same. So 0. And x is going to 0 from the positive side. Technically, they're both going in. If you write one of these, like x is going to 0, and they're the same, then clearly y is going to be going to 0 as well. Because they're the same. And then the third one we've already done. We're on the x-axis, so y is 0, but x is going to 0 from the positive one. Okay, so if we impose these things, let's see if we actually get 3 different answers. Maybe sometimes we get the same answer, sometimes we get different answers for all of them. So let's see. On 1, x is 0. So this is going to be the limit as y goes to 0. We put in 0 everywhere for x. So 0, 0, we'll get y divided by y. We'll put in x equals 0. And so then that limit is 1. I can cancel the y's as long as y is not 0, and in the limit I can do that, so I get 1. In the second one, x equals y. So now I'm going to get the limit as x goes to 0. What happens if I plug in x equals y? Well, y equals x. Doesn't matter. As I said, I'm going to use the limit of x. So if I plug in y equals x, on the top, I'll have 2x. On the bottom, I'll have x squared plus x. So I'm just replacing y with x. I get 2 copies of x on top, and I get this. Okay, so if I try and cancel, well, this one we probably could just use L'Hopital's rule on, but I know that, let's just go ahead and do that. Since we're now back in Calc 1, 0 over 0, we can use L'Hopital's rule. So I know that I get 0 divided by 0. So I take the derivative of the top, which is 2. I take the derivative of the bottom, which is 2x plus 1. And now what happens when I stick in x equals 0? The answer is this turns out to be 2 over 1. And I'm just subbing in x equals 0. And so the limit is 2. If I come in along this diagonal, the graph is supposed to go out 2 units, whereas I come in from the top, it's supposed to go up 1 unit. Trying to think about this in your head is really hard. I'm coming in this way, I'm supposed to hit 1, but I come in the other way, I'm supposed to hit 2. How does this even connect up with the origin? Well, the answer is it doesn't. Mathematically, it doesn't really help either because it's so broken that it's hard to see what's going on. Third one, just for kicks here. On the third one, y is 0 and x is going to 0. So we get the limit as x goes to 0. I put in 0 for y everywhere. So we'll get x and over x squared. Y is 0, so that part cancels out. So this one, let me just cancel one of the x's now. I could use L'Hopital's rule again. But if I just cancel one of the x's, x over x equals 1, which works because x is not 0 yet. So what happens is you plug in numbers that are bigger and bigger and bigger into 1 over x, the answer is this becomes plus infinity. And not only does the graph look like it's supposed to come into 1 height if you're coming in this approach, it's like a skateboard ramp here. We're coming in, we go up to 1. Okay, that's fine. We come along this skateboard ramp, we end up at 2. Well, that's not too bad. But if we come in from this side, the whole thing shoots up to infinity. So you probably wouldn't want to scale it. So anyway, clearly the overall limit does not exist. It's highly fractured at the origin. So probably won't come across these in real life, but mathematically we have to make sure that we've covered all of these things. The rest part of that section, which is sort of more technical, but it's not a bad thing to at least see, is the idea of a region being either bounded or unbounded. Which I think that's kind of common sense here. And then the other one is the difference between what's called an open region versus a closed region. If you want to be real technical on doing these limits properly, you have to know the difference between open and closed, for sure. And so I think it's just sort of easier to do a couple of examples here. And it's typically, and for the homework at least, it's talking about the domain. So for example, you might have had this. This is number 11. So here's your function, f of x, y. It's also good practice maybe, is 9 minus x squared minus y squared. Find the domain and then determine if it's bounded, unbounded, or open or closed. I haven't told you what those meant yet, but I think we'll see. as we do this, but the words do have some common sense. You do mean what you think they should mean. Okay, so I know if I want to define the domain, then I need to have what's inside the square root. It can't be negative. So it could be 0 or it could be positive. So non-negative. If we write this sort of in our technical form, it's all the xy pairs such that 9 minus x squared minus y squared is bigger than, or sorry, less than, right again. Need that to be bigger than or equal to 0. Just because we want to take the square root only of things that are non-negative like that. So if we rewrite this one more time, we get a set of all points xy such that 9 is bigger than x squared plus y squared. Now in a picture, you might be like, well, let's see, if they're equal, I get x squared plus y squared equals 9. Okay, I know what that is. That's a circle, radius 3. So that's if xy satisfy x squared plus y squared equals 9. If you wanted all the points that x squared plus y squared is less than 9, then that usually means that you're inside of the circle or you're outside of the circle. And so you can see that if you plug in, for example, 0 and 0, that works because 0 squared plus 0 squared is 9. So definitely that point is in there. If you plug in 1, 1, well, you get 1 and 1, that's 2. That is less than 9, so that point's in there. And any point that you plug in that's inside of the region here will work. So this is the domain. It's all points inside, and it's any point along the edge as well. So I could plug in 3, 0. I could plug in 0, 3. I could plug in the point on the edge here, which is like 3 square root 2 over 2, 3 square root 2 over 2. All those points work that should be satisfied. Now, if you look at this picture, would you say it's bounded or unbounded? Hopefully it's easy to see, well, this is just a bounded region. It doesn't shoot off anywhere. It's stuck in some area here. That's really common sense, the definition of bounded. If the region isn't sort of going out and out as far as it can go, it's like infinitely far, it's not bounded by some fence, then it's called unbounded. If it is bounded by some fence, it doesn't have to necessarily be a circle, but if it's bounded by something, that's called bounded. Closed and open, this is called closed because the boundary is included. And so as far as you're concerned, that's really what closed means, is that the edge, not only is it closed off by a fence, the fence is part of the region as well. So it's not like we're saying, well, I want everything but the fence. If you include the fence, it's called the boundary of the region. And so that's the definition of what's called bounded and closed. We'll try one more example and then take a break here. We might have something like this. So z equals 1 over the square root, let's make it bad here, y minus x squared. So what does that look like? We're talking about the domain. Well, I think the common sense way to write the domain, and you can start or even just leave it like this, is I want every pair xy, so you sort of read this as like the set of all points xy such that I know that I need to have y be bigger than x squared because I have a square root and there I got to make sure that the square root is positive underneath. It's strict greater than because I can't have y equal to x squared because if they were equal you'd have a 0 in the denominator. So this is a strict greater than symbol there. So what does that domain look like? I want every single point where y is bigger than x squared. So 0, 0 doesn't work, 1, 1 doesn't work, 2, 0 doesn't work, but like 0, 5 does. So we're plugging 5 and 0. 5 would be bigger than 0 squared, so that's not going to work. And maybe you look at this, you're like, well, let's look at what would happen if y was x squared, just to get the idea of this. That's the parabola, right? Squared. Put it in there as dotted lines just temporarily. Now, what does it mean to be not equal but greater than x squared? I want all the points where y is actually bigger than x squared. Well, everything on that line is where y is equal to x squared. If you want to be bigger, that just means you need to go higher. And so this domain is everything that is above the parabola. So it's basically above the parabola. And you can just plot a bunch of points and see which points work out. These points down here are definitely not going to work because y is negative, so that'll never be bigger than a square. All these numbers in here are positive for y. All these are positive for y, but they're not bigger than the square of the x coordinate. So everything above works. Everything on the parabola does not work because on the parabola y is x squared and we cannot have that. So y equals x squared is not included. And this is basically saying this is the boundary of the region that you're on. It stretches out infinitely far, so that's not included, which is another way of saying that the boundary is not included. So at least the domain is called open. And that's just the difference between those two. If it includes the boundary, it's closed. If it doesn't include the boundary, it's called open. Now, is this bounded or unbounded? Can you make a fence all the way around it to enclose it? And the answer is no, you can't because the region extends up the y-axis as far as you want to go. So because you can't draw like a fence around it, the domain is also unbounded. So we've got an example where it's bounded and closed, and in this case, it's unbounded and open. Yeah. So I think in the homework you taught some examples which are like exactly that, open or closed. Maybe it's neither one. Maybe part of the boundary is included and part isn't, in which case it's not open because it has part of the boundary, but it's not closed because it's missing part of the boundary. I think bounded, unbounded will be pretty clear as to whether it extends off to infinity in any direction or it's actually enclosed. So, get the technical stuff out of the way before we jump to the next thing. So we'll just take a quick break. Maybe we'll ask to see if you have any questions about homework at that stage before we start the next section. But come back just in about 5 or 6 minutes. So try and remember to hit record again. See you in just a couple minutes.